Thank you for coming. I know it's not an easy hour, so thank you so much for coming and for this invitation. So, and please do stop me if my handwriting becomes illegible. Okay, so I would like to start with some maybe rather well-known theorem, often called Tuke's theorem. That will be also a nice point to introduce the setting. So maybe for most of the talk you can think about y as being just the level 1 modular curve, complex points. But the way I want to look at it maybe later, you have some group G which will be in some inner form of PGL2 over Q, everything over Q today, and then we'll take this double quotient of the adelic points, define everything in a second. So K infinity is just a subgroup of G. This should be compact torus, okay? So there are two important cases: either G is split at infinity or not. So it's either it's PGL2R or it's Hamilton quaternions. So if it's PGL2R, just think about PSO2R maybe. And at least in the split, in the indefinite case, just a finite unit maybe of this maybe upper and lower half planes, because I work with PGL2 divided by some congruence lattices. So this is just C minus R. Okay? So that's the space where we live. So at the beginning, just think about this as being the regular upper half plane divided by SL2Z, if you want, the regular modular curve, level 1. So in this space, not all points are born equal. Some of them maybe are slightly more special, and we'll think about the Sem points. Okay? So we think about, and when we have a Sem point, so if you think about PGL2, not some inner form, this Sem point correspond to some Sem elliptic curve, and there's a similar picture in the other cases. And this always has some endomorphism ring attached to it, to this elliptic curve, which is unusually big. And we think that this will be denoted always by lambda. It will be some order in some imaginary quadratic field. Okay? And there's some more information maybe. And now this set of Sem points, you think about all Sem points for some fixed order lambda. So you fix an order lambda and you look at all the Sem points with this fixed order. You have this is some finite collection, and there is an action, I would like to say, of the Picard group. But because this K, okay, I didn't say what K finite is. So this is any compact open subgroup of the finite level. So I don't care about any level structure for this theorem. So this might be slightly bigger than the Picard group, depending on the level structure, if you're not even Hori level structure. So it's some extension of the Picard group, some finite compact abelian group. And so there are finitely many orbits of this in here, and just in the level 1, it's one orbit. And maybe I would like to define, just fix a Sem packet H in Y is a single orbit. So some order, each Sem packet will come with some order as a single peak lambda, maybe slightly bigger orbit of a point with Sem by X, with Sem by lambda. Okay, and maybe I should say that if you think about this case in G is indefinite at the real place, this is some nice algebraic variety, Shimura variety, or just a modular curve for PGL2, and this orbit becomes exactly the same as the Galois orbit. Okay, so if you're interested in Galois orbits, at least on this picture over Q, this is the same by the reciprocity. And that's this theorem, which has a long history before Duke and after Duke, but we name it for good reason. It's named Duke's theorem. So Duke 88, and there's a very significant input here from Ivanich in 87, which essentially deals with a definite case. Okay, Duke didn't prove the whole thing that I'm going to say. The statement is the following: is that so maybe I should say before I say the theorem, each such packet will always come with a measure. So each such packet is a finite collection of points. So the measure we'll have is just the finite counting measure, okay? And it's the only, if you like, all my measures this talk are going to be probability measures, Borel probability measures, and this finite counting measure is invariant of the Picard group. So it's you should see that it sounds trivial, but it has some non-trivial ramifications in the future. And it's the only measure having this property, okay? And I use the letter mu to denote it. So it's the normalized counting measure. And now you call it maybe the periodic measure. It's periodic for the Picard orbit, the Picard action. And so if I have a sequence, so each packet comes with an order, and each order comes with a discriminant. So when I say discriminant of Sem Point of a packet, it's the discriminant of the associated order. So if you have some sequence of Sem packets, this discriminants going to infinity, so I would denote discriminants. So discriminant here is a negative number. So okay. Then I would like to say that this period measures, they converge to the Haar measure, to the uniform measure, which is not exactly true, because I made this annoying choice of working with a non-connected setting. Otherwise, I would have to make an annoying choice somewhere else. So it's not true in general. Then I would say that the sequence mu I quasi-equidistributes. I'll define it in a second. Quasi-equidistributes. So what does quasi-equidistributes mean? So the complete definition will come slightly later, okay, when we generalize our language to where the definition will be easier. But it implies the following, that any weak star limit, so we are only interested about integrals on continuous compactly supported functions. Any weak star limit point of this sequence is a convex combination, so it's a probability measure of the uniform measures on connected components. But much more is known. You can actually understand which measure it is for your specific sequence of packets of the uniform measures on connected components of Y. So in particular, if Y were connected, it would just be converged to the Haar measure. Okay? So so I think Duke originally put this for level 1 and for the melting discriminants. Has a big generalization. A lot of people should be named, so I certainly won't be able to name them. I think maybe the final state of the art is due to Zhang in this setting, in this way of stating things. But so maybe some important historical comments, which are important also for what is going to come. So Linnik also worked on this problem in a different language, but completely equivalent. It's hard to date his papers. If you would like to discuss history, we can do this later. But in the 50s and the 60s, he developed his ergodic method, which seems to be very different from this method used by Duke, which I told you nothing about, which is the method using automorphic forms and non-trivial bounds on either Fourier coefficients or central values of L functions. So this is used it has some arithmetic input, but much weaker. And then it's somehow able to bootstrap this arithmetic input into something non-trivial statement. And what is the non-trivial statement? Essentially, what he is able to prove, you assume this. So this works for each sequence of discriminant. So what Linnik was able to prove, he needs to fix some prime, P1, such that and this will work only for specific sequences of discriminant. He needs that maybe slightly something more general is true, but this assumption is enough. That D is a quadratic. I hope I am correct. What you really need is that P1 splits at the Sem field. Okay, you need the splitting condition that for each Sem field the P1 splits there. And he was also he showed that GRH implies that this assumption is redundant. So splitting condition is redundant in his proof. So he was able to prove the whole theorem assuming GRH. And maybe to understand how this can work, both these statements are actually quantitative, not effective, but there is a rate. So the rate in Duke's proof is very good. In the correct way of measuring it, some polynomial saving in the discriminant. Here it's far from being that good and for reasons that we understand. But what happens, because there is a rate here, he was able actually to assume that this prime is not fixed, but it moves slowly with the discriminant, and then still his argument would hold. And GRH provides you a small enough split, and it's small enough to compare to the discriminant, so it wins when you compare to the rate that Linux achieved. So that's the way it worked for him. So this has some dynamic ingredient which we'll talk about later. So what we'll talk is about much more advanced version of a dynamic ingredient. Okay.
Explicitly formulate this thing, GRH?
Yes. I actually checked the papers. He formulated this certainly for the sphere. That's the paper that I read. He said more. He provided a specific zero for region, which is less than GRH, that provides exactly the rate that he needs. He was a very careful person in calculations. Yes. Okay. So maybe another thing to say that in this setting, this may not be so impressive for a modular curve. This implies the Andreault conjecture for a modular curve. So what the Andreault conjecture would say to us in this case, it says, if you translate it to this language, it says that if you take all the points in this union of your packets, there should be Zariski density in this curve. So here we have something much stronger. We have equidistribution, we have density in the complex topology, not just Zariski density. Okay? So now we are going from one modular curve, which is this is already a well-known fact, going to the situation if you have a product of modular curves, or maybe of some forms of Shimura variety. So products of Y's. Okay, no, that's not a good idea to lift it. So maybe I'll write it here so I have it for later. So I'm talking about products of Y's, and we have here a conjecture, which is going to remain unproved today. So this is the conjecture of Michel and Venkatesh. So what would be an analog of a Sem point? It would be maybe a point both of whose coordinates are Sem. Okay, and so let's state a specific situation. We'll start with talking about just X will be a product of Y with itself. Can make more general situations, product of n curves. This is good enough for us. And now you have, as before, some sequence Hi and Y with discriminants going to infinity. Now you should think about an interesting object inside Y times Y. So you can just take the product, but then nothing new appears, right? Everything reduces to the rank 1 situation. So you make an additional choice. So you for each I, you pick some element Ci in your slightly extended Picard group, and you define this joint packet. We're going to live now in X, which is Y times Y, to be able to point from Z sigma I acts on Z, where Z is in your packet. Okay? So if you think about it, you still have an action of your Picard group, but it only acts diagonally. So I use this delta up here a lot in this talk for the diagonal action, for diagonal embeddings. Okay, so this is the thinnest orbit you can think about it of special points. And you cannot expect this in general to equidistribute, because you could, this sigma I can be chosen arbitrarily, so this depends on sigma I, obviously. You can have always chosen it to be the identity. And then, okay, what will happen? You're just stuck in the diagonal embedding, right? And you equidistribute, but you equidistribute in this diagonal embedding by Duke's theorem. So you need some condition to say that this sequence is generic enough. So we are going to state it in a slightly weird form at the beginning. So you define this quantity Ni. What you're going to do, you take the minimum, you run over all integral ideals, integral and invertible. All my ideals are going to be lambda ideals, and they're going to be invertible. And you look only at those whose class in the Picard group corresponding to the image of sigma I in the Picard group. This is the real Picard group. And you look at the minimum of all norms. So it's some integer, some invariant of sigma I. And you require, the conjecture says that if, okay, not only the discriminant going to infinity, if this Ni goes to infinity, then the mu I joint, which I didn't define, but they are just the normalized counting measures on this thing, which is the Galois or Picard orbit of such a point. Then this mu I joint quasi-equidistribute. So what does it mean? It means, again, that some convex, any weak star limit is some convex. It implies, it means more, any weak star limit will be a convex combinations of the uniform measures and connected components. And this is already the product measures. So if y were connected, you just have that mu I joint should converge to if m is the Haar measure, m times m. So maybe I should not use this board, right? That's not a very good idea. So I'll continue here, excuse me. Okay, so maybe we'll try to understand what does this condition on an I means. So for this, we should talk a little bit about Hecke correspondences. So Hecke correspondence is, okay, a graph of a Hecke correspondence gives you some modular curve and some this product of y times y. Okay, and what happens if you think about it, if you fix a single packet, a joint packet, so a joint packet is going to be contained in quite a lot of Hecke and uncountably many Hecke correspondences. Okay, and at least if you think about all Hecke correspondences containing some packet H, so I remove the index here just for a fixed index containing some packet. At least if for maximal level, but otherwise just finite to 1, this for my maximal level this in bijection, otherwise it's finite to 1. It's in bijection with lambda ideals whose A, so lambda ideals again fractional ideals, whose class in the Picard group is sigma I, is the class of sigma I up to homotity, up to multiplication by Q star. And this norm, it will be very closely related to the degree of each Hecke corresponding represented by such an ideal. So whatever it means that the minimal degree of a mesogeny between two goes to infinity. If you think about this condition, it's only what you want to assume. So maybe give this a name, this condition. The fact that this goes to infinity, let's call it G, because this is what needs to be generic. So this G is equivalent to the statement that each fixed Hecke correspondence contains only finitely many HIs. Okay, so that's maybe a slightly less surprising way of stating it. Of course, if you have a Hecke correspondence which contains a sequence of HIs, these HIs will never equidistribute in the product space. They will just equidistribute in this rank 1 curve. Okay, so you can try and use this Hecke correspondence to get something good out of them. And this is a theorem of Ellenberg, Michel, and Venkatesh. Maybe before saying the theorem, I want to say something more about the conjecture, about its relation to Andreault. Okay, I'll go back to the theorem in a second. So again, we know Andreault for product of two modular curves. That's the theorem of André, I think from '98, and Edixhoven also proved it conditionally on GRH. And what does Andreault would say us for in this case? It will tell us that this, if you take the union of all of this packet, it will be Zariski dense again. And here again, we look for some much stronger property. We look at density and the complex topology, and even stronger, we look at to prove equidistribution. Okay. So in this case, this theorem of Ellenberg, Michel, and Venkatesh, well, they work in Linux framework, which is quite powerful for this. So they need to fix a single split prime. Okay. And they also need to assume another assumption. They need to assume that there is some positive number, let's call it eta, such that these ni's, okay, they go to infinity, but we don't want them to go to infinity too quickly. So we want them uniformly bounded by the discriminants, half minus eta. If you think about it, discriminant of the half is very close to the size of a packet, which is practically the class number, right? So this is something like h lambda 1 minus 2 eta plus little of 1, which is, this is Ziegel's bound. Okay? So why is this useful? Because what happens in this situation, at least in a very rough picture, your joint, this joint packet sits inside a Hecke correspondence of some relatively low degree. So if you're lucky, because it's of a b compared to the degree of the Hecke correspondence, you're by some version of a quantitative argument, maybe you can show that you're close to being equidistributed in this ambient Hecke correspondence, because this is now this is just a modular curve, okay? And now this ambient Hecke correspondence, because this ni do go to infinity, becomes equidistributed in the product space. So you can bootstrap this to equidistribute in the whole space. But this is really the limit. This type of inequality is really the limit of this argument. If you think about for any fixed eta, Duke's theorem said us that this invariant ni approximately equidistributes between 1 and d to the half. So for any fixed eta, this removes a big chunk of the class group, this restriction. And why should this be like a natural limit for this type of an embedding argument in some intermediate rank 1 curve?
Could you say again what the theorem is?
Oh, sorry. I apologize. Then conjecture holds. I'm only interested with this conjecture now. Okay, remember this ni is dependent on your choice of sigma.
This is not restricted to a product of two.
The way it was stated, it is. I think it's actually, I'm not sure.
If you need more factors, you need a better x.
If you take two split primes, I certainly can do it. If not, I need to think about it for some minutes, if I can do it or not, or if they can do it or not.
I certainly only thought about two.
Yeah. So if I take two split primes, I can deduce from it immediately, but I'll talk about it
The
later.
way we set up was really for two. I don't
Right, that's what I'm pointing that out.
I think the way I stated it, I hope it's all right.
So the conjecture is, you just
I stated for two, I will talk about more in a minute. Okay, I'll come there. So they prove the conjecture held by this type of arguments. Is that all right, Yanis?
For the role of pi,
P1. So you needed
there's a pi.
DI is the discriminant. Thank you for commenting on my impossible. Yeah, you have one fixed prime P1 and it's split in all the same fields. Let's think about this way. Okay. You'll see in a moment why it can be useful. I'll talk about this. And here you have this extra assumption that this minimal degree of isogeny doesn't grow too quickly. And then you can use this bootstrap some version of Duke into equidistribution in the product. Okay, so why you shouldn't expect such a thing to in the complementary region to this assumption when an I is approximately the class number? Why shouldn't? So if you think about this intermediate Hecke correspondence, its number of cusps, for example, should be approximately closely related to this Ni. Okay, so you are going to sit in something which have. You are going in a situation, it's just a heuristic argument, inside which the size of the Hecke correspondence may be the size of the packet much grow quicker than the number of cusps. So you have at most 1 point per cusp. There is no way you can expect this to equidistribute in the ambient space. Okay. So maybe let's come to the new results. Yes. It used not the theorem, it used the method of proof of the one copy case. And a quantitative version of the one copy case. It shows that you're equidistributed in this one copy, which is moving inside the product, and the copy itself is also distributed in the product. Okay, so that's the new theorem. So bear with me a little bit. We'll have, unfortunately, a few restrictions, and what I will try to do is to explain to you where these restrictions come from, why are they useful. So we are going to be in the same setting. We have x being y times y. We have hi in y, and we pick some sigma I, which defined as this joint bracket in x times x. And we also assume that the discriminant goes to infinity and then the sequence is generic, but no assumptions on the growth rate of Ni. And now comes the serious restriction. Also, maybe assume this is fundamental, but that's mostly for simplicity. Now you need to fix 2 primes. This is really essential to the method. Fix 2 primes and assume that we are split for all I, you assume for all I. That you're split at, your sequence, the CM fields are split at both primes. So primes that are distinct, obviously. So this is assumption number 1. And the second assumption, which is also going to be painful, you assume that the Dedekind zeta function of CM fields EI, so these are the fields where the orders live, this has no exceptional under 0, 0. Okay, and then conjecture holds. So we have these 2 significant assumptions. And you can remove each one of them and get some non-trivial statement about the behavior of these measures. And this non-trivial statement together give you the whole conjecture.
So you're still restricted to 2 here, can't you?
So, okay,
I mean,
thank you. I'm not. But I use this to deduce the so the following is a corollary, actually, of this theorem. I have here very... Thank you so much. So for me it was okay. This is something that Peter asked me some time ago. For me it was quite surprising to deduce the following: that now you go x, you look at n is some arbitrary integer. You take product of n of them, and now you, as before, you have hi in y with discriminants going to infinity. But now for each I you pick sigma I1 up to sigma I. You can do also more general, but that's good enough. In your slightly bigger Picard group, and you define the joint object now lives in X, in the product of n of them, and you define the way you expect. Z sigma I1 of z up to sigma I n minus 1 of z, where z is in the packet. And on it, you have associated to it this measure mu I joint, which is invariant under the diagonal action of your Picard group. So now it acts diagonally on all the coordinates to the gas. So this is, again, extremely thin orbit. It becomes thinner and thinner in the ambient space when you take n to infinity. So I need to state the genericity assumption, which can be painful in the language I used before, because there are much more options. But here's an easy way to say it. If you have something which is equidistributional product of two things, you certainly you necessarily need that the projection to each two coordinates will equidistribute, right? And the projection to each two coordinates of this object is exactly an object of the previous theorem, or the previous conjecture. Okay? So you assume that the projection to each pair of coordinates, so you have like j not equal k between 1 and n, satisfies the genericity assumption. Okay? So that's certainly necessary, and it's also enough. Then 1 and 2, so 1 and 2 is you have them here, the splitting assumption in 2 primes and the assumption about lack of exceptional vehicle implies quasi-equidistribution. So this joint measure, in the connected case, for example, it will be the product measure of all n copies. So maybe I say that, again, Andre Oort would say to us that this, again, this Picard orbit is a Galois orbit, and Andre Oort exactly would say that this Picard orbit is Zariski dense, and here we get something much stronger, at least when these assumptions are satisfied, which is highly non-trivial. But I remind you that the proof Peel approved in about 2010, right? Andre Oort for arbitrary products of modular curves. It's certainly not a corollary of the n equal 2 case. And here, because this category of measures, or say algebraic measures, in some sense behaves nicer than algebraic varieties from, to deduce from projection to 2 to it comes to the question that if you, yes?
Anthony, why do you have a CM field in the statement of the theorem?
These are all, so HI is a packet of Sem points still.
Not a CM field.
So the Sem field, I mean, is just the quadratic extension. Yeah, that's the quadratic where the order lives. So it's the most boring type of Sem field over Q. Okay, thank you. So yeah, so here this will come down to the statement. So there is a use of some non-trivial machinery here, but it also comes down to for algebraic group, for algebraic reductive group that sits in a product of n. If you know that the projection into a 2h factor is everything, then it must be the product everything, which is certainly not true for algebraic varieties. So that's what makes this work. Okay, this I want to leave, so maybe we can go here. Okay, so I'm done stating new theorems. I would like to tell you something about the proof.
So do you now believe a more general conjecture with lots of factors, with 1 and 2 being unnecessary?
Oh, I certainly believe in it, and believe in a much more general conjecture, which will follow for some very fancy other conjectures. That
the generalization is just that when you project any 2 factors.
yeah. There is also there is some conjecture for a general conjecture for Shimura varieties, that if you have some sequence of special points, then there are Galois orbits in the limit should in this language quasi-equidistribute. And I'll talk in a moment about toral periods. You can say a conjecture about adelic toral periods in any product, in any quotient space of reductive groups. If it's generic enough, you expect it to equidistribute. This is not really something we know a lot about. Yeah, conditioned. Let's put it like this. Maybe you should say that Linik proves his theorem, that's why I talked about it, that GRH allows you to remove the splitting condition. Okay, GRH will give you two small split primes, but there is an ingredient about which I will talk here, an ergodic theoretical, which at least at the current moment is not proven in a quantitative form. It will be not an easy task probably to prove it in so much simpler statements are not yet known in a quantitative form. So it should take some time to get there. Even so, under some certainly believable assumptions about quantitative statement homogeneous dynamics, this should imply already the conjecture under GRH, but we are not here with that.
To clarify a point, I think Sheldon already proved under assuming GRH for products of any number of terms, but this is a much stronger statement in that you're giving topological density rather than Zariski density. That's the big, or topological equidistribution in particular, topological density was much stronger than
Yeah, in C.
Zariski.
Okay.
In the case of a definite quaternion also equal.
Yeah, G can be also a different quaternion. My statement, the way I wrote it, the state. So you can also get, for example, this statement. When you work out exactly what it means, you get the statement for super singular reducted, super singular at P reduced modulo P.
And there do some steps in the proof simplify in a definite case.
It will be completely. You see the methods completely don't see it. So the algebraic, the method won't care about at all about the Galois structure, about the fact that it's algebraic variety. So the way I stated why these orbits are Galois orbits only in indefinite case, right? The definite case is that some orbits of some Picard groups, they are not Galois orbits anymore.
Is it a topological statement, even if imagine that's easier?
Let's put it like that. Both Elon and myself thought about it and were not able
I see.
to do it.
Isolation type statement.
We were not, yeah. But maybe it is easier by some. That's the only thing I can say about this. It doesn't sound it sounds reasonable that it might be easier, but no luck there, unfortunately. But I would not rule this completely. Okay, so maybe the first step I would like to do is completely forget the finite level situation, go to the adelic language, because some things will be much more obvious there, what's going on here. So we're going to adelize the whole picture just because it will be easier to describe what's going on. So we really want to think just about this GA over GQ. So all the proof will live here, or in objects like this. So from here you have your projection to Y just by dividing by your compact group. Okay. So you want to lift you have here some packet H now for fixed index, and you want to lift it here into some meaningful way, such that it will project to this thing. So what happens is that if you have I'm not going to describe this construction, but it's quite elementary if you work out what's going on. So if you have your packet, each fixed packet will give you some pieces of data which you can extract from it. You get a torus in G. It's a maximal Q torus, which I require that it will be anisotropic over R, or in other words, that TR is compact. Okay. And you get some adelic element that satisfies the following property. You'll see in a second why it's so useful. So this adelic element, it has an Archimedean part and some finite part. So this always satisfies this point, that if you conjugate your real torus, your real points, at this G infinity, it's actually, remember I already fixed some compact torus. We had some compact fixed torus K infinity. So it's always this K infinity. So from this packet you can extract such two pieces of data. And then from this, you'll get the following nice set. Look at the coset of this torus by G, and then you can project to YA. So when I put the square brackets, I just mean always the projection to YA, maybe to some adelic quotients, which will be obvious. So this is some set, which we'll call the adelic packet. And when you take the projection map by dividing by your compact group, you actually get your original packet. Okay? So that's the relation between these CM packets and torus orbits, which is obvious in the adelic language and not so straightforward. So this set is invariant under an action of some very nice group. So what acts on it? G inverse T adel G. So this is some closed set. It's invariant under the action of this group, this nice locally compact abelian group. And when you project down, you exactly get whatever is left of this action, you get an action of the Picard group by Hecke correspondences. So this is what gives you the action of the Picard group, but now slightly more straightforward. Okay, let's continue here. Straightforward to see what's going on. Now, if you look at on this set HA, just as a topological space for a second, this is the same. So this G plays a huge role when describing the location of this set inside this ambient space. But by itself, it's just TA over TQ. So there's a T invariant probability measure on it, a unique one. Remember, our T was R anisotropic, so it's a particular Q anisotropic. So this is a finite measure space. So there's some invariant probability measure on this, which is T invariant in this picture. So it's invariant under G inverse TG in this picture. So there's a unique, so denoted by mu, the G inverse TA G invariant probability measure on HA. And because of all of this invariance property of the counting measure, the Picard group on this under the torus, when you project, you get exactly your counting measure. So we actually would like to prove that this sequence of measures will, okay. So for example, for Duke's theorem, you would like to prove a slightly stronger theorem that this sequence of measures equidistribute in some sense in the product, in this adelic quotient. So in order to say this exactly, let me introduce one more simple object. So we have this quasi-equidistribution. What really happened is this problem with this, that we are not simply connected in my language. So we need to look on this group. This is the image of the simply connected cub. So if PGL2, this is just SL2, okay? So this has finite index at each place. So it's in some sense not much smaller. And we say that any measure, let's say lambda, this is a measure on YA, and also the second case we'll discuss is YL times YA, is quasi-invariant if it is, in first case it's just GA plus invariant, and the second is the product of these two groups invariant. So if it were invariant under the whole group, it would be necessarily the unique Haar measure. So what it says that this measure behaves as the Haar measure on anything which is orthogonal to the residual spectrum. And what happens for the residual spectrum is actually much easier to understand because it's only questions about abelian groups. So this is so you would actually Duke's theorem, for example, would say that the associated packets converge to a quasi-invariant measure. Okay, and from here you can get everything you want. It's better to continue. You can erase this. So now we need to analyze the whole joining question. This will really clarify the usefulness of the split primes. So bear with me a little bit. So the joint packets, joint adelic packets, okay. Now you need to pick another element. You need to pick some S in T adel. This is the guy which corresponds to the sigma in the Picard group. Okay. And using this S, you can define a joint adelic packet. So very soon I'll stop writing this A inside YA times YA. So what you do, you embed your torus diagonally into G times G. Okay. And then this thing will be T diagonal adelic points, G as G. So S commutes with the torus. So if you think about the projection to each coordinate, it will be just your usual pocket. But it twisted in a non-trivial way in the product because of this S, which is exactly the sigma we saw before. And this also, there's some joint measure on it, which is invariant under G inverse T at del G, everything acting diagonally. Again, this acts diagonally because it commutes with this S. And you want to show that under the genericity assumption stated correctly, this mu joint quasi-equidistributes in the limit, is quasi-invariant in the limit. Now, so what is the splitting at P1 and P2 give us? You can use this splitting assumption to reduce your question to the following. So there's some reduction here. I mean, like logical reduction, not reduction, not something. And what is this logical reduction? You can fix some additional data. You can fix AP1 in GQP1 and AP2 in GQP2. Split tori such that, and now the useful property appears. For each I, we'll have an equality of groups. GPK, and for each also K in 1, 2. GPK inverse T of QPK. Now, think about it for a moment. All of this depends on the index. I don't write it because I'll go crazy if I put I's everywhere, but all of this data depends on the joint pocket. It depends on the index, okay? And under the splitting assumption, you can arrange things that is all the same torus. So this depends on I, and this is a priori, and this is fixed. So if all pockets are split under some fixed tori at two places, then any weak star limit measure will be invariant under two split tori at different places. And this is an extremely powerful information. So I don't know if someone were here at the most lectures in 2015. Elon Lindenstrom's gave a lecture about a theorem of his and Eisendler about joinings of tori. So that's what we are going to use here. So we are going to state a corollary to the theorem, which is more general than what I'm saying, of Eisendler and Lindenstrauss. So when this theorem was proved, one of the main motivations was to tackle this conjecture. And you see where it fails to tackle, and I'll try to explain what you do to overcome this difficulty, which is the main new part. And the conjecture is, they say the following. You take any probability measure lambda on YA times YA. And you can also make products of n products here for this theorem and still work. So that's where, okay, whose projection to both coordinates is quasi-invariant. So that we get for our measure from Duke's theorem. So we use Duke's theorem and we know that the projection to each coordinate is quasi-invariant, but we don't know what happens upstairs. To each coordinate is GA plus invariant. So any such measures, any measure whose projection to GA plus invariant and lambda is invariant under split torus at two places. So the two is really important here. This theorem is plainly wrong. The obvious counterexamples when it's one place. Okay, if you just assume, then okay, it's not going to be a very easy statement. Lambda is a convex combination of nice measures. So what are the nice measures? Let me continue over there. So how much time do I have? Okay. So just from this theorem, we know some information. It cannot be some arbitrary measure which is supported, let's say, if you think about the real manifold on some set of fractional Hausdorff dimension, something horrible like that. It essentially can only be a convex combination of what you want with measures which are closely related to the measures on Hecke correspondences.
Find the positive entropy.
So you get the positive entropy here for free in some sense. Okay, we don't know what entropy is maybe now, but so this fits into this framework of measure rigidity for toral actions with positive entropy. Positive entropy and much more is for free here because you assume that each projection to each factor is already quite. So that's very. You expect this to be true without this assumption, but okay, we don't know much. That's far away.
Yeah, I'm just pointing out that some people might melt in the form of positive entropy.
Thank you. Yeah, so this assumption is tailored inside this statement. Thank you. Okay, so what are the possible measures? So it's a convex combination. One is what you want, G times G A plus invariant measure.
Yes,
Yes. This
this is the joining version of it.
is what they call joining rigidity theorem. So what you want, and 2 is what you don't want. So you're going to so these measures are going to be some generalization of Hecke correspondences. So you're going to fix some extra data. So you look at the following sets, which are similar to our packets. Let's call such a set J. It will depend on psi, which will be in a second. So instead of embedding the torus diagonally, you can embed the group G diagonally. So you can look at G delta A plus psi, where psi is any element in G times GA. Okay, so this is some closed subset, which is, let's say, if psi, for example, were rational and some twisted, will project to a Hecke correspondence. In general, some translate, if you would like, in the correct language of this Hecke correspondence. So this has also an invariant measure. So Nick psi is the psi inverse G delta A plus psi invariant measure. So a significant distinction maybe from classical Hecke correspondences is that this comes in a uncountable family because of problems that we can also translate the Archimedean place. You are not K invariant, K infinity invariant. So your convex combination of this and some of this. So it's some combination of these measures of this uncountable family of measures. And what we really need to show is to show that none of these appear. Okay, and I have.
But your finite combination.
No. You don't know that.
So what do you mean by convex combination?
It means that there is a measure on the space of measures, probability measure. Yeah, a Borel measure. You can think about it as a Borel measure on the psi's. Or maybe on, if you think about it, only care about cosine of psi by G delta A plus. So a Borel measure, which is maybe less scary. But in general, it's a measure on the space of measures, which is not that bad. It's a matrix over a locally compact space. Yeah, you have really left the algebraic domain here. And also, this works for any reductive group or for any perfect group. So G, not just for PGL2. Okay, so maybe I'll draw to you a picture, try to understand. Let's try to exclude the case psi equals identity. So we're just trying to exclude the situation that we have some positive mass on the diagonal on y delta embedded in y times y. So this is already non-trivial by itself. And the moment you're able to do that, you're able to do the general case, essentially. That's as difficult as the general case. So let's think about psi equals identity, which is just the measure of this on this. So I hope I'll be able to say something non-trivial about that. So let me draw a picture. So imagine that's my modular curve, R mod Z, just for simplicity. So that's my product of two modular curves. So this is my packet. Okay, I need 4 to make it believable. And I want to exclude this situation. So what am I going to do? I'm going to draw a small bow around each point. And I have a measure on this. This is the knee, the one-dimensional measure. And I'm going to measure what is the mass of each ball with respect to this measure knee. So most balls have 0, but some have a possible contribution. Okay? And I'm going to average this contribution over all the points. So my first definition of a correlation So mu is my measure on a packet, and ni is my measure on a Hecke correspondence. But you can think about now as any measures for this definition. And what is B? B you should think about as a resolution. This is this bow. So this is just some identity neighborhood generally in E. Okay, so maybe a definition is here. Sorry for the mess. So definition number 1 is just you look at the measure of the following in the product space of this set. You take 2 points, each pair of points in. So x and y both belong to y squared, because it's mu times ni. And let's also assume maybe that B is symmetric to make this definition symmetric and mu and ni. And you look at the only at points which are close to the diagonal in B times B. Because, right. And you're going to shrink this ball and see how this behaves when the ball shrinks. Okay, so maybe let's think when mu is the Haar measure, is m times m. With any measure that you would like. Then you know exactly how each ball shrinks. Each ball with respect to the Haar measure is exactly shrinks the same rate. So whatever measure you put here, it always behaves something like mb squared. Okay? Is that clear? Now, for Hecke correspondence, it's self-correlation. Okay, this is a one-dimensional object in our language, so it's like mb. So if you have any Wigster limit, let's say mu I, and let's say we are able to prove that correlation of mu infinity with your fixed Hecke correspondence behaves up to some constants like what you expect from the Haar measure. Then you immediately deduce that it is singular to this Hecke correspondence. Because if it were bigger than some constants times ni, this would be bigger than some constants times m of b. And you can take m of b as small as you want, and you get that. Okay, so we didn't even, okay, this is trivial. So you need somehow a way to measure this correlation. So you measure this correlation for a single packet, and what turns out, the only thing I'll be able to say to you, that this thing is actually, if you write out down the expression for this, this is essentially a relative trace of some form. Okay? So this is just d mu x, d mu y, where this is the standard homomorphic kernel on the product space. And f is just the characteristic function of your ball. If you write down what it means, it is almost the same thing. Because in order for x to be in the b times b ball around y, there needs to be some lattice elements which translates x to be near that. So up to things high in the cusp, this is practically the same. Now this thing has a geometric expansion. Because this measures mu and ni actually sits, mi is on the torus and ni is on g delta. So this thing has a geometric expansion. And you can analyze the relative orbital integrals and rewrite it as a shift. Understand this actually, yeah, that's somehow maybe one half of the difficult point that I'm not going to talk about. Understand this is actually equal to a shifted convolution sums of some sort, which is related to the Dedekind zeta function. But this shifted convolution sum is a function extremely short, its range. So whatever standard analytical methods for harmonic analysis is not going to be useful. So the only thing that saves you is a sieve method, which is close to work of Shiu and Nair, and what you see in the paper of Rudnik, Sarnak, and Bourgain about the sphere. So this short range, the only thing that you're able to do is apply sieve method to the shifting convolution sum after you extract it from here. And the way you extract it is you interpret this as some intersection numbers in the correct sense. And when you apply sieve method, unfortunately, in order to control the error terms, you need to assume this lack of Landau-Ziegel 0. So because you get some logarithmic average. And logarithmic averages in short intervals are exactly the error terms controlled by the existence of Landau-Ziegel zeros. So that's maybe not extremely useful in this time frame. But I hope at least the theorem and the main obstacle to proving it are at least explained. Thank you.